Welcome to this talk. I'm Niall Murphy. My colleague here from Google is Chris Jones, and we'll be giving this presentation on service levels and error budgets. In some respect, this is reasonably well-trodden ground or more fundamental type material, so there may be some of you for whom this is not new. Do feel free to type in your laptop or whatever you were going to do anyway. Let's crack on. I guess the agenda is as follows: to talk about service levels, agreements, try and separate out agreements, indicators, and objectives, because today, even today in the industry, they're still somewhat tangled. And thinking about why decoupling those concepts is useful, why this is a useful intellectual framework to understand the behavior of your service and how you could improve it. How you should choose SLIs, service level indicators, and service level objectives. And also talking a little bit about what this means in practice. I suspect the most relevant piece here would probably be the notion of decoupling penalties, which is one of the things that's implied in service level agreements, from the idea of having objectives or indicators. That decoupling is quite powerful, actually. So, a couple of introductory words first. Today, I lead ADS, Site Reliability Engineering in Dublin, Ireland, which is about 70, 80 people. Chris is working on App Engine, SRE in SFO. We have a book, it turns out. Thank you. This talk is from that book, chapter 4, as it happens. We are having a book signing tomorrow at 12:30 after the Who/What is SRE panel. So please do turn up if you want to ask questions, etc. Since this is actually a fairly substantial contributor volume, it's key to point out that it isn't just me and Chris, it's also John Wilkes, Cody Smith, and Mark Roth, who have contributed to that chapter as well. So, what is an SLA? An SLA is essentially, we will provide this for you, XOR, we will compensate you in some way. Remember that word, compensate. That implies lawyers and management and a number of other things that are maybe less tasteful. It's not so relevant to engineers as such, except in two specific contexts. First one is that management likes to set priorities. Speaking as a manager from time to time, I do this. But also engineers get to tell other people how much it'll cost to move from one reliability level to another, and that also informs priorities by management. We won't put too much more time into this, but it is the overall context for what we're saying here. So generally we run software systems for the benefit of users. We're not just running software systems because we like to run software systems or it's fun. Okay, well, maybe for some of us, that's why we run software systems. But when we're being user-oriented, we're doing it because we're trying to provide a service to folks. It's very important to understand how good a job you're doing at providing that service. And so we need to understand what the user is trying to do, what their problems are, and the numbers or the performance of the service that matters to them. It's also important to remember that users also often end up caring about widely disparate and actively contradictory things, which we'll go into in a moment. So, one list of things that users care about up there: latency, how long it takes to actually perform an action, the error rate, how often it fails, throughput, availability, and so on. All of those are pretty crucial properties of a service. One I wish to draw your attention to briefly at the bottom is correctness. So users don't really care well if they receive an extremely fast, well-formatted list of wrong things when they're trying to use a service to achieve something. This is maybe a little bit controversial in the domain of SRE because what we touch in Google is often in the domain of infrastructure. So we are thoroughly engaged in getting the machine to respond quickly, and we don't care so much about the data quality, except from the reliability angle, we actually care quite a lot about the data quality, but that is often the domain of the product development teams. We do, as we talk about a little bit in the book, have some, in SRE, we do often have some kind of alerting based on, oh, it turns out I'm shipping 50% of the data to production that I did 4 minutes ago. Like maybe this is bad, or there's some kind of data correctness issue coming on here. So we should also talk about indicators at this stage, definition of indicators. An SLI is some number, some metric indicating the level of service. There are a lot of numbers that you could have about what your service is doing. IOPS per second, number of machines actively engaged in servicing this request, so on and so forth. We are drowning in lots of numbers. Only some of them are as important and as reflective of the general performance of the service that you would actually want to select them as an SLI, however. So it follows that we can have too many indicators, or at least we can have enough of them that it's confusing. So we do need to focus on what we choose. Another interesting question is the question of where these are measured. So classically in, we'll say, web services, there is server-side and client-side latency. You can often make the mistake we have in Google of measuring more at the server side because that's where we happen to have the locus of control or the locus of measurement, rather than the client side, which is actually more indicative of what the users are experiencing. So that is a key point. Another point is once you have a metric, you have a place where you're collecting it. You believe you understand what it means. It's a question of over what period this metric is measured. We look at that graph over on the right-hand side, and we look at the thing which is actually happening and the measurement interval over which we are collecting that data and aggregating it, I guess is the word. The general point being that the resolution of the collection and aggregation really strongly affects our interpretation of this data. At a 1-minute sampling interval, for example, that over there looks like a fairly steady stream of requests with nothing particularly interesting about it. At a 30-second sampling interval, however, we see that, in fact, it's quite uneven with a lot of spikes. And maybe at a 1-second interval, we might see that all of our requests come in at the beginning of the minute, and nothing else happens for the other 59 seconds. So, two things, if that hypothetical situation was in actual fact happening, two things would be affecting our understanding of the service there. First one is, A, perhaps our clients are synchronized somehow, which would be important to understand, and also I probably don't have to tell this group important to fix, as in make it not synchronized. And secondly, that the system may well come to be dominated by peak performance, that if you have all of your clients hitting at one moment, you need to scale or behave in a very different way than if you can smear out your clients throughout some larger time period. So it has implications for capacity planning, implications for monitoring, implications for speed of reaction, and in general, how we think about the system's behavior. So your aggregation interval is really, really important. So another key point, again, which is highly relevant to how we do things in Google, is the question of averages over distributions. So averages, in general, are misleading, okay? So the average human has 1.9 legs, or whatever it is, right? So that actually doesn't tell you that much useful, I guess. Think about the graph over there. So this graph shows the 50th and the 80th and 90th and 95th percentile latencies in milliseconds, okay? And furthermore, the y-axis is on a log graph. So the median latency is around 50 milliseconds, and the 95th percentile is around 5,000. So there's kind of a 100 times higher differential there. So I think the interesting thing about that graph is that looking over this time period, the median latency hardly budges at all, okay? The high percentile latencies, on the other hand, are actually spiking quite wildly. And remembering that this is a log graph, there's actually a significant difference between the low spikes and the high spikes in those 90th and 95th percentile graphs. So we often care more about the long tail / 95th percentile behavior of a system than we do about the mean or the median, particularly in the case of services which have high fan-out. What do I mean by that? I mean that if we have a request of some kind coming into a system, we're talking more about interactive stuff rather than batch stuff. If we have a request coming in and it talks to a number of other back-end servers in order to construct some kind of response, if there is a high latency for some proportion of those requests, and it ends up taking up resources for a long time on some of those backends, the actual effect on the system as a whole is much larger, which means that if for example, we'll take a search request, which might need to contact, as I'm saying, a number of large backends. If one of those backends happens to be blocked by high latency responses, you can end up taking out capacity in that backend group at a higher rate than you would normally, which means your chance of cascading failure is increased, which is something you want to avoid. So that article there, Jeff and Louise, the tail at scale is illustrative in this context. So something else we should talk about, I guess, is the commonalities in how we measure things, how we talk about things in the service level indicator world. We can abstract out a lot of the commonalities and the verbosity of referring to these strings, these properties that we're trying to measure. For example, HTTP get latency measured at the client by a black box prober every 10 seconds over all tasks in a cluster, blah, 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 blah. If we just refer to these as simply client-side get latency or client-side post latency or some summarization, rather than having to specify everything all the time, then we'll be more efficient in our communications and our representation of what's actually going on. And now I hand over to Chris.
So now that we've covered service level indicators, let's talk about service level objectives. Fundamentally, a service level objective is simply a mathematical relationship. Service level indicator is less than or equal to a target, or service level indicator is between a lower bound and an upper bound. And we could use a service level objective as input to a control loop, right? If we start out measuring a service level indicator. Next, we look, is it within the bounds? If yes, we don't need to do anything, keep on rolling. If no, we need to figure out what action we need to take in order to re-achieve that target. We repeat the process, and ideally we profit. There are a couple of things that we need to think about, though, in the process. First, SLOs set expectations for system behavior. People first want to know what kind of performance or availability, et cetera, that the system provides in your documentation. But if you don't publish that, your users will expect whatever performance they're getting right now will continue indefinitely into the future, which really constrains your options. Similarly, when setting SLOs, don't pick targets based on your current performance. It may not be representative of what you can do in the future under whatever changes you might want to make. Second, saying that your system will be infinitely scalable or always available is a mistake because it won't be. Third, think about keeping a safety margin, a little bit of a buffer, just in case, because things will inevitably go wrong when you're operating a real system. Finally, don't overachieve. If your system is, in practice, more reliable or more robust than what you actually document, people are going to come to rely upon that. So we've actually had systems at Google that intentionally take downtime if they haven't had any by whatever random mechanism in order to remind people not to rely on them more than they're allowed to rely on it. Finally, you should be keeping track of an internal SLO target that's a little bit tighter than what you publish externally. That's that buffer that we talked about. Because that gives you some space to respond to chronic low-level conditions that are causing errors. And it also means that you can change the implementation of your system in order to make different performance and cost trade-offs in the future. And that turns out to be really important if you have a system that's growing, right? Jeff Dean likes to say, plan for 10 times growth with your current system. But when you get to 100 times larger, you're going to need to redesign it completely. Let's get philosophical for a moment. Why are we here? I'm going to be a little heretical. SRE's job is not to maximize reliability. If you think your job is to maximize reliability, then it's really easy. You say no to any changes, and you go on vacation. And hopefully everything will still be running the same when you get back. Instead, we need to think about reliability as a property of a software system. And it's one property, and as Ben Traynor likes to say, it's probably the most important property for a lot of systems, right? If you don't have a system that works, well, it's not really good to anybody. But there are also other features, other properties of a system that are important to users. Bug fixes. People would like their bugs to be fixed. People would like to have new functionality, sometimes. So on. Because we run software systems to serve users, and users want many things, we can't just focus on reliability. Similarly, our organization would like many things besides just a 100% reliable system. We might like to actually run it at a lower cost. We might like to simplify how it's designed so that we can actually maintain it and keep it running in the future. So what we think of as SRE's job is to maximize product velocity and minimize costs for a given level of reliability. We want to try to get as many of the things that we want as possible, recognizing that we can't get everything we want. That implies that the optimal level of reliability is not 100%. As the philosopher Jagger once said, you can't always get what you want. So how then can we figure out what reliability we need in the system? Well, it's a product question. We need to figure out what the cost of building a system that will hit a particular level of reliability is, and then ask ourselves, prioritizing, is that the best thing that we can do for our users? And sometimes it doesn't. But fundamentally, that is a management question for your product management and your engineering management to figure out. What SRE can do, however, is measure how reliable your service is, figure out how to improve the reliability, estimate how reliable the system will be after those improvements, figure out how much it's likely to cost to do this, and then work with product development to actually implement those things through improving the code base, standardizing infrastructure across different products, using things that are already built, building monitoring systems, and so on. Now that we've accepted that we don't want all of the reliability that we can have, we can use error budgets. And what those allow us to do is to figure out how much failure we're allowed to have. Because remember, we said we don't want 100% reliability. We only want like 99.9%. So we have 1.1% of requests in a month, say, that we can use to do whatever we want. That means that we can say, all right, we're going to roll out new software and see if it works. Maybe it does, maybe it doesn't. Or we can change how we implement things in the back end. Maybe that works, maybe it doesn't. The point is, once we've agreed on that target, we can then feed this into a control loop, just like before. We measure the reliability. If our system meets those reliability targets, go ahead, release more features. Release them as fast as you can. Once we hit the point where we're no longer reliable, under whatever terms we've agreed with in advance, stop. Work on stability and reliability. Go back to step 2 and keep doing this. We can then use a continuous version of this where we look at how quickly we're running out of budget, right? We can look at how much reliability we're using up over time and use that to control how quickly we get out of, we release stuff, where we focus our time, rather than doing sort of bang, bang control where we go between features and no features, or releases and no releases. Critically, though, SRE needs to have the authority to halt launches which will exceed the error budget. You need strong support from product management and from executives. What this ends up meaning is that SRE is no longer in the business of saying no. Instead, we say yes if you do this, or yes when this happens, given pre-agreed conditions. Product developers no longer want to circumvent SRE in order to get things to production faster, so that would be counterproductive to their goal of getting things out. And it means that reliability is now viewed by the product development organization as a first-class feature of the product. End result, much healthier relationship for everybody. So, things to remember. First, use SLIs to understand the service's key metrics. Second, use SLOs to specify how good the service needs to be. Third, use error budgets to control release velocity. And I don't know, do we have time for questions, Liz? Nope. No questions, sorry.